over 200 tons. They blast off every 2 minutes, cruising at close to the speed of sound. They are among the most complex and powerful systems on Earth, yet we take them for granted. Now, commercial jets on Modern Marvels. Everett, Washington. In the spring of 1967, it was 700 acres of rock and timber. In a little more than 6 months, it would be transformed into a high-tech city, populated by an army of highly skilled men and women that would eventually total 20,000. Commissioned by the Boeing Aircraft Company, their mission was simply to build the biggest and fastest subsonic commercial jetliner ever constructed. It would carry over 350 passengers at over 600 miles an hour. Its name was 747.
The 747 really was a quantum leap in capacity and capabilities that if you were planning the growth of an industry in a logical, progressive way, you probably wouldn't do that. You probably wouldn't grow an airplane 150% larger than the one that came before.
Boeing President Bill Allen assigned Vice President Mal Stamper to head the 747 project.
Allen said, "How would you like to build the biggest airplane in the world?" And so Stamper, he leaped to it, you know, and he moved his bed up there.
The 747 project demanded the design and construction of 270,000 tools. But the first tools that went to work on the original jumbo jet were not welding rigs and rivet guns. They were chainsaws and bulldozers. So big was the project that no building existed that could house it. One would have to be built. 780 acres of forest were cleared 45 miles north of Seattle, next to an abandoned World War II airfield. A 2-mile spur of railroad track had to be added to the main rail to move building materials up to the plant site. 34,000 tons of steel arrived by rail for the initial construction of the 200 million cubic foot structure. It would become the biggest building in the world. Later, the same track would be used to bring in the gigantic sub-assemblies from 20,000 contractors in all 50 United States and 8 countries around the world. The total assembly would require over 4 million individually numbered and cataloged parts. The project would take 5 years, $5 billion. It would consume 10 million engineering man-hours and 14,000 hours of wind tunnel testing. The first designs dated from 1965, when Pan American Airlines president Juan Trippe bankrolled the project with a $250 million down payment for 25 of the monster planes. By the spring of 1967, the giant sub-assemblies began to arrive while plant construction was still underway. Boeing employees called it the aluminum avalanche. Stamper's rugged 747 team was also given a nickname.
Stamper called them the Incredibles. They wore Paul Bunyan stickers on their hard hats and their lunch pails, and they wouldn't go home at the end of the shift.
Working around the clock, the Incredibles struggled to meet the 1969 deadline, when the first 747 was due to roll off the line.
And it all comes down to a certain point on the factory floor where the first center section goes in, and then all the parts begin to flow into it.
That flow began with the massive wings. After being assembled in huge fixtures called jigs, they were joined to the enormous center section made of titanium. Each wing, with its 37 degrees of sweep, measured 120 feet in length, 26 feet in width, and was 7 feet thick at its root. 52,000 rivets went into the assembly of each wing. The overwing section of the fuselage was then fitted to complete the center section. The brute lifting in the plant was performed by 26 overhead cranes that traveled on 39 miles of networked track. Their combined lifting capacity was 1.9 million pounds. Next, The nose and forward body sections were lifted into place and joined to the center section. The 747 was the first design with the cockpit up above the deck, 29 feet above the runway. The aft body section followed, complete with galleys and lavatories. The jet's cavernous airframe was completed by the tail cone, horizontal stabilizer, and vertical fin. The tail assembly stood 63 feet above the deck, the height of a 6-story building. Once all fuselage sections were bolted and riveted into one gigantic shell, the landing gears were installed to allow the big bird to be moved down the line on its own feet. The landing gear was comprised of 4 separate sections of 4 wheels each, plus a nose gear with 2 additional wheels. Cargo holds, seats, wall and ceiling panels, and in-cabin entertainment equipment were added at this stage. The final items included radar antennas and landing gear doors. As the project proceeded, a major problem became obvious. The 747 had a weight problem. Various modifications to the original plans were adding weight at an alarming rate. The original 550,000-pound design weight had jumped to 710,000 pounds. The Incredibles fought back, using composite materials and titanium instead of heavier materials. The 8,500 pounds of titanium alone yielded a weight savings of over a ton. The diet worked, and the project continued. The final step was the installation of the Pratt & Whitney JT9D3 engines, each capable of producing 43,500 pounds of thrust. Once all components were installed, they were tested and retested. The fuselage was pressurized, and all pressure seals were tested again. Once the testing phase was completed, the giant bird was towed to the paint hangar, where 300 gallons of paint added another 1,200 pounds to its maximum empty weight. Finally, the customer's insignia, or livery, were added to the plane's exterior. By 1969, all the questions had been answered except one. Would it fly? At 11:34 on February 9, 1969, that question was answered with an unqualified yes. After the usual debugging process inherent in any new plane, the 747 went into commercial service on January 22, 1970. Since the first prototype rolled out in 1969, more than 1,300 747s have been produced. 3 decades later, the 747 is still the biggest and fastest subsonic jet in the air. Since its entry into commercial service in 1970, approximately 1.6 billion passengers have flown on a 747. The 747 fleet has logged 20 billion miles, the equivalent of 42,000 trips to the moon and back. Next, the pioneers of jet power, the engineer and the test pilot. The first manned flight by Orville Wright in 1903 covered a distance of 120 feet. This equals the length of one 747 wing. Commercial jets will return on Modern Marvels. The Wright brothers' first manned flight in December of 1903 ushered in the era of powering fixed-wing aircraft with internal combustion piston engines. For almost 2 decades, aircraft engine builders accepted the conventional wisdom that any increase in power would come from more over 200 tons. They blast off every 2 minutes, cruising at close to the speed of sound. They are among the most complex and powerful systems on Earth, yet we take them for granted. Now, commercial jets on Modern Marvels. Everett, Washington. In the spring of 1967, it was 700 acres of rock and timber. In a little more than 6 months, it would be transformed into a high-tech city, populated by an army of highly skilled men and women that would eventually total 20,000. Commissioned by the Boeing Aircraft Company, their mission was simply to build the biggest and fastest subsonic commercial jetliner ever constructed. It would carry over 350 passengers at over 600 miles an hour. Its name was 747.
The 747 really was a quantum leap in capacity and capabilities that if you were planning the growth of an industry in a logical, progressive way, you probably wouldn't do that. You probably wouldn't grow an airplane 150% larger than the one that came before.
Boeing President Bill Allen assigned Vice President Mal Stamper to head the 747 project.
Allen said, "How would you like to build the biggest airplane in the world?" And so Stamper, he leaped to it, you know, and he moved his bed up there.
The 747 project demanded the design and construction of 270,000 tools. But the first tools that went to work
of the jet engine in the early 1930s, and had been ignored by his government, given really, not ridiculed, but really not given the attention that it should have been.
Meanwhile, von Ohain's work drew the immediate interest and support of a leading German aircraft builder, Ernst Heinkel. In 1936, Heinkel financed von Ohain's development of a jet engine prototype. By 1939, von Ohain's engine was being married to a swept-wing fighter airframe. And in August of that year, just 1 month before the Nazi invasion of Poland, the HE-178 became the first jet-powered aircraft to fly. In England, Whittle's work was finally getting serious backing from the government. This new focus was brought to the attention of a visiting American Air Force general. In March of 1941, General Henry Hap Arnold was on a fact-finding visit to England. America was not yet in the war, but the U.S. was looking for ways it might help the British. Upon seeing Whittle's engine, Arnold saw an opportunity to help England and get his country into the jet age with one giant leap. He immediately made arrangements with the British government to have Whittle's W-1 engine and research shipped to General Electric Corporation at Lynn, Massachusetts. His purpose was to allow U.S. aircraft builders to study it as part of the war effort. Boeing and several other airframe makers were invited to study the W-1 and submit plans to incorporate the new engine into a viable high-speed, long-range military aircraft. 6 years and many design hours later, Boeing parlayed this knowledge into the B-47 bomber.
The B-47 was really the most important multi-jet bomber in history. From the B-47 came not only the 707, the KC-135, and the B-52, but all the Boeing designs.
Whittle's engine design was not the only technology that made the B-47 such a revolutionary aircraft. Boeing's access to German swept-wing technology, captured in the final years of the war, was the second part of the coup. Boeing's wind tunnel was the third.
Boeing got started with the B-47, as I mentioned before. It was a $13 million project, and it's probably the best $13 million that anybody ever invested. But the B-47 had a 35-degree swept wing.
After thousands of wind tunnel tests, Boeing learned that as a straight wing approaches supersonic speed, a layer of air builds up along its leading edge, increasing drag. The leading edge of an angled or swept wing is able to slice through the air at high speed, delaying the buildup of this unwanted layer. The U.S. had beaten England to the punch in the production of large military jets. In the years after the war, the British were determined to be the first in the air with a jet-powered commercial aircraft. At the time, America's Douglas Aircraft Company ruled the commercial skies with their piston-powered DC-3s, which carried 90% of the world's air traffic. The Americans seemed content to continue making jets for military use only. In 1949, Britain's de Havilland Aircraft Company stunned the aviation world with the unveiling of a sleek 93-foot-long jetliner prototype with 20-degree swept wings and 2 Whittle-designed jet engines buried in each wing root. It was christened the de Havilland Comet. It could carry 36 passengers and a crew of 6 at a cruising speed of almost 500 miles an hour, 50% faster than the fastest piston engine plane. 3 years later, in 1952, the first comet entered commercial service. But within 2 years, 2 comets had crashed. After exhaustive investigations, it was determined the comets crashed because of explosive decompression.
The comet had square windows, which seems innocuous enough when you think about it, except that a square is a point at which a fatigue failure can start more easily than a round window. And in fact, that's what happened with comets. Very, very tiny cracks occurred at in the corner of the windows. And once they occurred, it was just like ripping open a gigantic bag. It just blew apart because the inside differential pressure was so great.
In the years it would take to recover, Britain's lead would be taken by the Americans and never regained. Next, the Americans build the first truly successful jetliner. At any given moment, there are approximately 40,000 commercial jet passengers in the skies over North America. Commercial jets will return on modern marvels. The post-war prosperity of the 1950s brought increases in personal income. Consumers were able to afford the things they wanted, and one of the things they wanted was travel. In 1951, Boeing President William Allen traveled to England with his top engineers to witness one of the first test flights of the Comet. He was impressed with the basic concept, but felt the scale of the plane was all wrong.
So when Boeing saw the Comet and decided that they'd better get into business, the big consensus at Boeing was to advise their president, Bill Allen, that they could build not only a jet airplane, but they'd build one better than the Comet.
Allen knew that jets were the future. Still, he was reluctant. All previous Boeing commercial transports had been unsuccessful.
They lost money on the 377, they lost money on the 247, they were simply not in the business. Douglas, on the other hand, was in the transport business. The airlines loved them, they had a wonderful relationship with them. Everybody flew DC-3s and DC-4s and DC-6s and DC-7s.
In Boeing's favor was the experience it had gained on producing the jet bombers B-47 and B-52. But Allen knew his company couldn't survive on military contracts alone. On April 22, 1952, Allen rolled the dice and sank $15 million, a quarter of the corporation's net assets, into the development of a new jet transport. It began life as the 386-80, but would eventually be renamed 707. Failure would mean bankruptcy. Success could mean riches and a giant lead in a new market. Learning from mistakes made by de Havilland, Boeing knew that the fuselage would have to be able to withstand thousands of cycles of pressurization.
What Boeing did was they built a big tank, water tank, 100 feet long, 20 feet wide and 20 feet deep. And they built an entire fuselage. And they put this fuselage in the tank, and they pumped water in and out over a period to simulate cycles of flight. So based on that information, a whole new set of design criteria was developed for long life pressurized airplanes. That's where it all started.
Going back to what they had learned on their large bomber projects, Boeing engineers designed the Airliner with swept-back wings angled at 35 degrees. Instead of placing the wings at the top of the fuselage, they created a low wing design. The 707 was designed to carry 130 passengers, more than 3 times as many as the Comet's 36. Its 4 turbojet engines were pod-mounted out on the wings rather than buried next to the fuselage. This design would prevent an engine fire from spreading into the cabin. The cruising speed was 535 miles per hour. The airframe was subjected to 4,240 hours of wind tunnel testing. The fuselage was reinforced with titanium tear stoppers to guard against stress cracks.
In other words, if you're going to get a crack, you don't want it to run and become catastrophic. You want it to stop. So they built what they call crack stoppers into the design.
The first 707 was air tested on July 15, 1954. It passed with high praise from the pilots. In 1955, the U.S. Air Force ordered 29 of the planes, but still, there were no orders from the airlines. Finally, a few orders trickled in. Then suddenly, out of nowhere, Douglas Aircraft Company delivered a startling announcement. They would build a similar jet called the DC-8. The crafty Donald Douglas had waited for Boeing to commit to the 707 design. He announced to the airlines that the DC-8 would be larger than the 707, with 6 abreast seating rather than 5. The DC-8 was nicknamed the paper airplane, since it was sold while still on the drawing board.
And the interesting thing was that such was the airline's love of Douglas, and such was their confidence in Douglas, that they were willing to buy DC-8s before they'd even got off the drawing board almost, even though they had a 707 flying.
Boeing's Bill Allen had too much invested to let Douglas trump him. While continuing to sell his original 707s, he ordered his engineers to widen the fuselage by 16 inches and install more powerful Pratt & Whitney JT4 engines. This second version of the 707 was called the Intercontinental, and it truly was. It was the first true long-range commercial jet. The airlines and the flying public loved it.
People got on board the airplane, could not believe how quiet it was, how smooth it was. I mean, they were flying above the weather, you know. There had never been previously in commercial air transportation a similar forward leap. This was an entirely new notch that Boeing had achieved.
Over at Douglas, the company rushed its paper airplane into production, knowing they had to get it right the first time. The grueling production timetable almost wrecked the company.
Unfortunately for Douglas, they didn't have the management. They were an older company, and they had run into management and production difficulties, so the DC-8 really overstressed them.
Once the long-range transcontinental market had been conquered by 707s and DC-8s, the airlines began to ask for short-range jets that could provide economical jet service between major cities in Europe and the U.S. Jets that could service airports with runways too small for the 707s.
Well, the next major step, I would say, is that at that time, small jets weren't economical. The challenge to the industry was to build an airplane, a jet airplane, that was smaller.
European plane makers tried to fill this market with several designs that carried less than 100 seats. But it soon became obvious that larger payloads and more power were needed, especially in America.
United insisted that the airplane operate out of Denver with good results. United has Denver as a hub, and Denver is a mile high. So the criteria for taking off and landing an airplane at Denver is much different than at sea level like Seattle or Los Angeles.
Denver's thin atmosphere required a plane with extra power at takeoff. Airports with short runways like LaGuardia demanded a jet capable of steep, quick descents. The airlines wanted one plane that could handle both.
Now, each airline had a particular requirement. Now, United wanted a shorter haul airplane to operate more economically over shorter range distance, and Eastern wanted it. United wanted a 4-engine airplane, Eastern wanted a 2-engine airplane. So Boeing had to come up with some kind of a compromise, and the really deciding a tough factor was that Eastern's airplanes had to lift off a 4,860-foot runway at LaGuardia and fly to Miami nonstop.
Boeing's team of 1,000 engineers looked at over 150 design studies and evaluated the airline's requirements. On December 1st of 1960, Boeing's president William Allen stepped up to the table once again and bet the ranch on the new design. It would be called 727. It would use the same fuselage width as the 707, providing 6 abreast seating for 120 passengers. It was powered by 3 of Pratt & Whitney's new JT-8D turbofan engines, which produced 15,000 pounds of thrust each. Together, they could easily launch a loaded 727 into Denver's thin, mile-high skies.
A 3-engine jet instead of a 4-engine jet, there are a lot of obvious advantages. You cut down on your inventory costs right away with a 3-engine jet. You cut down on your fuel costs with a 3-engine jet compared to a 4-engine jet.
But the technology that put 727 in a class by itself was its wing. The 727 wing was sleek and aerodynamic at altitude for speed, and thanks to a unique design of multi-layered retractable flaps, it could expand its surface by 25% when landing and taking off. This greatly increased the plane's ability to navigate short runways.
This was the first time in industry history where they had split the flap. And it turned out that this is exactly what the doctor ordered. It's like when you see a bird land and feathers all come out. Well, there's a lot of feathers that come out on the 727.
When the first 727 rolled out on November 27, 1962, Boeing engineers discovered that it was 15 knots faster than the wind tunnel tests had predicted. It consumed 10% less fuel and could carry greater payloads than anticipated. When the 727 went into commercial service, it rapidly developed a reputation as a pilot's plane. Its responsive handling characteristics were praised as being more like those of a small fighter than a huge airliner. But this reputation would prove a source of trouble for the new jet. After 19 months in service, 727s began to experience approach crashes. With 4 accidents in 8 months, the ghost of the comet began to stalk the halls of Boeing's headquarters. The Civil Aeronautics Board immediately launched an intensive investigation of the jet's flight characteristics. In each case, the verdict was the same. The pilot had miscalculated the descent, trying to fly the tri-jet by the seat of his pants. These findings served as a grim reminder of what all pilots have been taught. Jet airliners must be flown by the book, not by pilot instinct or feel. With its reputation restored, the 727 would go on to become one of the best-selling commercial jets in history. 1,831 sales had been recorded when production ended in 1984. Next, size versus speed. Jumbo meets Concorde. Dwight D. Eisenhower became the first American president to travel by jet. He commissioned a 707 to be the first jet-powered Air Force One. Commercial jets will continue on Modern Marvels. From the mid-60s on, the air passenger market continued to splinter and subdivide into smaller and smaller niches. The viability of these operations are calculated by subtracting ticket sales from fuel burn and maintenance costs. At the very heart of this equation is engine power. In 1965, Douglas Aircraft fielded the first American twin jet, the DC-9. It was a 90-seat short hauler with engines in the rear. Douglas had improved the tail design, giving the twin jet greater stability. The DC-9 used 2 huge JT-8D Pratt & Whitney engines. That gave it a range of 1,923 miles and an economical advantage over the tri-jet 727. Airlines were impressed. Orders rolled in.
So it becomes very advantageous, and it leads inevitably to the airplanes we're seeing today, the big twin jet 757, 767, 777s, because if you have fewer engines, it's much more economical.
In the 1960s, the greater use of computers began to have a significant impact on aircraft design and operation. Probably the most profound of these was the development of autopilot computers that could actually pilot a plane. Using data acquired through many sensors, flight control computers automatically adjust the aircraft's control surfaces and engine operation to achieve optimum altitude, speed, and fuel efficiency. The computer's ability to process large amounts of flight-critical data allows it to fly the plane with a degree of precision no human pilot can match. Still, in emergency situations, no computer has ever replaced the instincts and skills of a well-trained, experienced pilot. The 1960s also saw the birth of 2 of the most significant and controversial commercial aircraft ever to fly. One would shatter all records for speed, but fail to turn a real profit. The other would set a new standard for size and bring air travel to the masses. In 1962, Sud Aviation of France and the British Aircraft Corporation joined forces to produce a commercial aircraft that would travel at over twice the speed of sound, Mach 2.2, or roughly 1,450 miles per hour. London would suddenly be less than 3.5 hours from New York. The radical Delta body craft was named Concorde. The Concorde's power came from 4 rear-mounted Olympus engines. Total thrust was over 150,000 pounds, twice the output of a 707. But political bickering and multiple design changes slowed Concorde's inception. It would take 8 years before the first prototype would be ready to fly. But the news of the supersonic jet would have an impact across the ocean in the U.S. Pan Am and Boeing had joined forces on the first wide-body jumbo jet, the 747. What many people did not know was that right from the start, the 747 was designed as a cargo plane. The wide-body spaciousness was not originally designed for passenger comfort, but rather to ensure that the hold could accommodate 16 two-abreast 8x8 cargo containers. Later models were designed with an upswing nose door to allow straight-in loading. The motivation for all this cargo consciousness was the Concorde. In most aircraft design circles at the time, it was believed that soon all passenger travel would be done in the supersonic jets. They believed that all subsonics, including the 747, would eventually be relegated to freight duty. History would prove them wrong.
The problem with supersonic transport is not in the marketing idea. Everybody who's flown across the Pacific Ocean wants to get there a lot faster. Unfortunately, the technology involved is just too expensive, and there's not enough market for it.
Fearing America would be left behind, the Boeing company, at the urging of the government, began work on their own supersonic transports, even while the 747 was in production. In March of 1969, the first Concorde test flight took place in Toulouse, France. The plane was behind schedule and over budget.
The Concorde had hundreds of millions of dollars of R&D that were just simply written off. But they could never, ever begin to recover the cost, and they knew it early. They knew it well on. They could have saved money by stopping the programs, but they couldn't do it because of national pride.
Airlines began to shy away from the 118-seat payload, fearing ticket sales could never offset operating cost. The designers increased the airframe to hold 136, but still the airlines stayed away in droves. The Europeans tried everything to show off their plane.
They've had some demonstrations in which a 747 and a Concorde would take off at the same time. The Concorde would fly to Europe, land, load passengers, and fly back and land back at the starting part before the 747 landed in London.
These demonstrations hurt rather than helped, proving that fuel burn for a transatlantic Concorde flight was 20% greater than that of a 707. Some scientists were also claiming that the high-flying plane would damage the ozone. Another major hurdle was noise.
People didn't want you flying supersonically over the continent and shattering windows everywhere.
The phenomena of sonic boom occurs when an object overtakes and collides with its own sound. This creates a shock wave in the atmosphere similar to a clap of thunder.
There has been no solution found or even hinted at for eliminating sonic boom that would allow it to across populated land masses. So you have to fly it over the water, it's got to go long distances, and it's going to be very expensive to fly.
Boeing's SST made it as far as the mock-up stage before the project was killed. The Concorde was relegated to a high-speed charter service for the wealthy. Though it had been a financial fizzle, it had taught the European plane makers that they must join forces to compete with the Americans. Next, a glimpse into the future of commercial aviation. A commercial jet's cockpit voice recorder, often called the black box, is actually bright orange. Commercial jets will return on Modern Marvels. After 20-some years of dominating the commercial jet industry, Boeing awoke in the 1970s to find its position being challenged from all sides. The period was called the Wide-Body Wars. Douglas Aircraft in California and the McDonnell Aircraft Corporation of St. Louis had merged to become the McDonnell Douglas Corporation. This merger had produced the DC-10, a 380-passenger jet. And from across the ocean came the A300 from Airbus Industry.
Airbus came into being roughly 30 years ago as a result of the various European manufacturers at the time essentially ending up competing with each other, and none of them doing a very good job of making any money. They all built fine airplanes, but to go up against the giant American companies at the time, they felt that the only way to be fully competitive was to join forces.
As Airbus was gaining ground, McDonnell Douglas was faltering. A series of accidents dogged the DC-10. The flying public lost confidence. The plane was doomed. It would later be redesigned and called the MD-11. By the late 1980s, only Boeing and Airbus were serious contenders. Using the best and the brightest aircraft designers in Europe and state-of-the-art computer technology, Airbus began to grab larger and larger shares of the world market.
Airbus has, over the past 30 years, has developed a product line that covers practically every niche required by today's airlines, from small airplanes, roughly 100-seat, up to 4-engine airplanes of 400 seats or more.
Airbus soon set its sights on Boeing's 737 with its A330, a twin jet with a 267-seat payload. It followed with its 4-engine A340, a 376-seat jetliner, a worthy rival to Boeing's 767. Boeing was now in a fight to protect its market. The American giant's first response was to stretch the 767 body, but this approach was discarded. In 1990, Boeing took another great risk and chose to design a whole new family. It would be called 777. It would be the most ambitious project since the 747. The technology used would change the way planes are designed and built. The 777 would be the largest twin jet ever built, with a payload of up to 550 seats. The design would take place on a worldwide digital drawing board called CATIA. It would comprise 7,000 workstations in 17 time zones.
The CATIA allowed us to design on the computer and design 3D models on the computer, assemble the entire airplane in terms of its three-dimensional characteristics, all of the modules and the tubing and the wire runs and the entire airplane on the computer.
With the CATIA workstation grid, a worldwide team of designers and fabricators could work on this digital three-dimensional blueprint simultaneously.
So for the first time, anywhere, anytime, an airplane was totally designed by computer technology. Now this 777 was a $5 billion, 10,000 engineer, 5-year program to do that.
In order to accommodate the new production line, Fortress Boeing would have to be expanded. The biggest building in the world was increased by 275,000 cubic yards. The renovation used enough steel to build the Empire State Building twice. To meet the 1994 delivery date, over 240 companies in the U.S. and 11 countries around the world worked simultaneously to produce the 20,000 sub-assemblies required for the 777 project. The 20-foot, 3-inch wide fuselage was built around a skeleton of carbon composite floor beams and aluminum alloy ribs called stringers. The outer skin was made from a new Alcoa aluminum alloy called 2XXX that has the highest fracture toughness of any metal now used in this application. The most critical technology on any twin jet is engine power and reliability. Since the 777 would be flying transoceanic flights, each of its engines had to be able to carry the aircraft by itself should the other engine fail. The engines were the most powerful jet engines ever developed. Pratt & Whitney, Rolls-Royce, and General Electric all supplied engines for the 777.
Previously, the highest thrust engine on our airplanes was on the 767, around 60,000 pounds of thrust, and we wanted to enter service on the 777 with at least 74,000 pounds of thrust and a view of growing that to 90,000 pounds of thrust.
The wing spans almost 200 feet in length and a top surface area of 4,628 square feet.
I think one of the major elements of this 777 is the advanced technology in its wing. The airfill sections of the wing are the most advanced on any commercial airplane. We've used our computer fluid dynamics analysis tools and a lot of wind tunnel testing to develop that wing shape.
On June 12, 1994, the first 777 took to the air. A year later, it won the prestigious Collier Award for Outstanding Aeronautic Design. In the minds of many, it has put Boeing back in the lead in the commercial jet field. But for how long?
Certainly the 777 experience is how everybody that can afford to do it and has the capability to do it will do it in the future.
What is the future? How much bigger? How much faster? How long will the 3-decade-old 747 remain the queen of the skies? One answer will come from Airbus industry. In 2006, the European consortium plans to roll its A3XX, a double-decker jumbo, larger than the 747.
The 747 is older than Airbus industry. It's time for a new airplane to be built with state-of-the-art technology from the wheels up. And that's what will happen with the A3XX.
With $10 billion in development, the A3XX will boast a 555-seat capacity with 3 classes of service. It also may provide passengers with luxuries never before seen on any airliner, such as gyms, theaters, and other frills.
Airlines will be able to, at their choice, to put in certain other amenities if they want to put in small lounge areas, if they want to use the lower deck area for bedrooms, for duty-free shopping, or for other facilities that they think might be appealing to their passengers.
Will A3XX become the design standard for the next 35 years? Only time and technology can tell. One radical alternative for the future is currently being researched at the NASA Space Center at Langley, Virginia. This futuristic super jumbo concept is known as the BWB, or blended wing body. The designers of this delta-shaped flying wing of the future are working on ways to carry 800 passenger payloads across oceans at speeds of 560 miles per hour. Many experts believe that airport design will not be able to keep pace with such quantum leaps in aircraft size and capacity. Commercial aviation has come a long way in a very short time. One of the driving forces in this technological explosion has been an intense competition among a worldwide field of high-stakes players. But ironically, with mergers and takeovers on the rise, the future commercial jet industry may be a world where competition does not exist. Some experts predict, because of staggering development costs, that the 2 remaining giants, Boeing and Airbus, will merge into one international plane-making monolith. But whatever the future holds, we can look back at the past century and know that commercial jets have changed our world. They have carried billions of us to distant lands and helped foster an international exchange of ideas, trade, and culture.
Descended from royalty, counseled by angels, chased into a strange land by murderers, and adored by a son who would grow up to be called the King of Kings. Who was the mysterious spouse of Mary and father of Jesus? Joseph, the silent...
Later, the same track would be used to bring in the gigantic sub-assemblies from 20,000 contractors in all 50 United States and 8 countries around the world. The total assembly would require over 4 million individually numbered and cataloged parts. The project would take 5 years, $25 billion. It would consume 10 million engineering man-hours and 14,000 hours of wind tunnel testing. The first designs dated from 1965, when Pan American Airlines president Juan Trippe bankrolled the project with a $250 million down payment for 25 of the monster planes. By the spring of 1967, the giant subassemblies began to arrive while plant construction was still underway. Boeing employees called it the aluminum avalanche. Stamper's rugged 747 team was also given a nickname.
Stamper called them the Incredibles. They wore Paul Bunyan stickers on their hard hats and their lunch pails, and they wouldn't go home at the end of the shift.
Working around the clock, the Incredibles struggled to meet the 1969 deadline, when the first 747 was due to roll off the line.
And it all comes down to a certain point on the factory floor where the first center section goes in, and then all the parts begin to flow into it.
That flow began with the massive wings. After being assembled in huge fixtures called jigs, they were joined to the enormous center section made of titanium. Each wing, with its 37 degrees of sweep, measured 120 feet in length, 26 feet in width, and was 7 feet thick at its root. 52,000 rivets went into the assembly of each wing. The overwing section of the fuselage was then fitted to complete the center section. The brute lifting in the plant was performed by 26 overhead cranes that traveled on 39 miles of network track. Their combined lifting capacity was 1.9 million pounds. Next, the nose and forward body sections were lifted into place and joined to the center section. The 747 was the first design with the cockpit up above the deck, 29 feet above the runway. The aft body section followed, complete with galleys and lavatories. The jet's cavernous airframe was completed by the tail cone, horizontal stabilizer, and vertical fin. The tail assembly stood 63 feet above the deck, the height of a 6-story building. Once all fuselage sections were over 200 tons, they blast off every 2 minutes, cruising at close to the speed of sound. They are among the most complex and powerful systems on Earth, yet we take them for granted. Now, commercial jets on Modern Marvels. Everett, Washington. In the spring of 1967, it was 700 acres of rock and timber. In a little more than 6 months, it would be transformed into a high-tech city, populated by an army of highly skilled men and women that would eventually total 20,000. Commissioned by the Boeing Aircraft Company, their mission was simply to build the biggest and fastest subsonic commercial jetliner ever constructed. It would carry over 350 passengers at over 600 miles an hour. Its name was 747.
The 747 really was a quantum leap in capacity and capabilities that if you were planning the growth of an industry,
bolted and riveted into one gigantic shell, the landing gears were installed to allow the big bird to be moved down the line on its own feet. The landing gear was comprised of 4 separate sections of 4 wheels each, plus a nose gear with 2 additional wheels. Cargo holds, seats, wall and ceiling panels, and in-cabin entertainment equipment were added at this stage. The final items included radar antennas and landing gear doors. As the project proceeded, a major problem became obvious. The 747 had a weight problem. Various modifications to the original plans were adding weight at an alarming rate. The original 550,000-pound design weight had jumped to 710,000 pounds. The Incredibles fought back, using composite materials and titanium instead of heavier materials. The 8,500 pounds of titanium alone yielded a weight savings of over a ton. The diet worked, and the project continued. The final step was the installation of the Pratt & Whitney JT9D3 engines, each capable of producing 43,500 pounds of thrust. Once all components were installed, they were tested and retested. The fuselage was pressurized, and all pressure seals were tested again.
In a logical, progressive way, you probably wouldn't do that. You probably wouldn't grow an airplane 150% larger than the one that came before.
Boeing President Bill Allen assigned Vice President Mal Stamper to head the 747 project.
Allen said, "How would you like to build the biggest airplane in the world?" And so Stamper, he leaped to it, you know, and he moved his bed up there.
The 747 project demanded the design and construction of 270,000 tools. But the first tools that went to work on the original jumbo jet were not welding rigs and rivet guns. They were chainsaws and bulldozers. So big was the project that no building existed that could house it. One would have to be built. 780 acres of forest were cleared 45 miles north of Seattle, next to an abandoned World War II airfield. A 2-mile spur of railroad track had to be added to the main rail to move building materials up to the plant site. 34,000 tons of steel arrived by rail for the initial construction of the 200 million cubic foot structure. It would become the biggest building in the world.